Okay, perfect. All right, I'm gonna give one more minute. Same thing as last time. They didn't have an adapter that works from VGA to the laptop. So we're gonna be doing it through screen share. So I posted the link on the Piazza. The beginning of class actually won't require any screens, so that'll be a surprise demo. Yes, and thank you all of you for your bad dad of the joke submissions in the intro form. Yeah, I promise all of these have been coming from you guys. I thought this one was particularly meta, so I wanted to use it as the last one. All right. Okay, cool. So this lecture is kind of exciting. So first, welcome to the last lecture of CS106L. It's been such a nice, a long journey and a nice journey. But yeah, we will get to that. But first, thank you guys for voting on the final lecture topics. If I could get a drum roll. Yes, thank you. The final topic that was selected was multithreading. It was actually very interesting. Every person except for one actually selected multithreading as a topic they wanted to cover. So I was, pleasantly surprised. Close behind that were makefiles, which we won't have time to get to today. So instead, I'll just post up a PowerPoint that has sort of what we would have presented about makefiles. So yeah, you guys can peruse through that if you're interested. All right. Okay. So since this is the last lecture, I thought we'd also try something fun and interesting in the meantime. So can I get 3 volunteers? All right. I see 2 and a 3rd. All right. Ready? You're gonna come up to the front. This will take maybe the first 5 minutes or so of class. All right. So before we jump into threading today, one thing that I really want to give you an idea of is why is multi-threading important at all? So to give a bit of a background, a lot of times when people think about multi-threading, what they're actually thinking about is multi-processing. They think about something like a lot of parallel computers in data centers or something like that, where they can run sort of operations at the same time. But multi-threading sort of has a different use case. For example, let's say that we have only a single computer that has a single CPU. Why would we do multi-threading in that case? Because it seems like in that case you can still only ever run one thread at a time. So what is the point of multi-threading? And so to give a sort of motivation for why multi-threading can still be useful even in that case, we're going to be doing this live demo. All right, so the demo of the day, what's going to be happening is, let's see, who wants to be writer number 1? All right, Eva. So Eva's task is to write the numbers 1 through 10 on the board. Okay, so you won't start yet. The way this is going to work, and then, okay, so let's say we have another writer who wants to be the other writer. Okay, perfect. Zach is going to be writer number 2, who is also trying to write the numbers 1 through 10 on the board. The thing is that I'm going to be the controller that decides who gets to start writing when. So I'm going to tell Eva, when I say Eva's name, she's going to start writing, and she's going to write as quickly as she can until I stop her, and then I'm going to get Zach to write. Okay, ready? So let's give this a demo. Oh, right, sorry. So you only get 1 piece of chalk, because, again, we only have 1 CPU. All right, Eva. Zach. Eva. Zach. Perfect. Amazing job. Was that easy, hard? Thumbs up, thumbs down. Okay, awkward, but not too bad. Okay, so again, we're sort of back to the problem of like, why would we use multi-threading at all? Right now we have 2 different threads, but only a single person can control the chalk at any point in time. So now we're going to introduce the wildcard element. All right, Brian. So your role is the role of random number generator. And so what's going to happen is that Eva, as writer number 1, when she reaches the number 2, she's going to have to stop and wait for you to give a random number to her. And then she's going to have to write that random number and then finish writing the rest of the numbers through 10. Okay, So the thing is though, Brian, you are very, very let's say glitchy. And let's say you take a really long time to come up with what random number you wanna say. It's a very important question. All right, let's do this again. Eva.
7.
Ah, too short. Let's do it again. Let's do it again. Even longer. Even longer. You're very sleepy today. All right, Eva. Eva.
10.
There we go. Okay, so the entire concept is that while Eva has to wait for this input from Brian, Zach could have been writing that entire time. And so, sort of like a cute demonstration, what is the purpose of having multiple threads in a single CPU? Can anyone tell me?
Oh,
Any
so
of our
one
nice
process
writers?
has to like wait for something, the other process can keep going while the other process, well, the first process is waiting.
Absolutely. So that's really the key idea. Good job. Let's give a round of applause for our live demo participants. Yeah. So a really common question that you might ask is, okay, how often is it though that you actually have to be waiting for something in a process? It turns out a lot more often than you might think. For example, any time that say you're reading from a file from a disk, you have to wait for that disk to be found. There's a whole lot of sort of physical things that go into it. Or say you're trying to write a request to a website, then you have to wait for the website to respond. So these sorts of delays take place all the time. Even in something that we've seen before, something even as simple as cin, we have to wait for user input to come in. So waiting actually takes place in a lot of places, and that's sort of the reason why multi-threading as opposed to multi-processing is also a thing. So that's sort of the general scope of what we're talking about today. So back to our slides. How many of you guys have seen multi-threading before or heard of it? Okay, got you. So actually a decent amount. So I'll just go through this beginning part relatively quickly then. So for anyone who's unfamiliar, the concept of a thread is sort of exactly what you saw just now. In the past, actually in this class, and for a lot of you in all the code that you've written up to now, your code has been sequential, meaning that once you execute one line of code, then the next line of code follows it, then the next line of code, and so on. And so what threads are is they're a way to parallelize execution. In this case, in the case of a single CPU, they're not truly in parallel. There's not two things happening at once. But you can imagine that the result might feel like they're parallel. And we'll get into more of that in a bit. So for a bit of a graphical representation, you can imagine that we have one program running. And let's say that program generates two new threads, let's say our two writer threads from our demo. And in the meantime, of course, our main program is still running forward as it would have otherwise. And then at some point, all the threads join back together, and our program outputs whatever result it wanted to output. So there's a couple of tricky things with multi-threading, and there are probably some things that you guys can already sort of guess might be tricky issues. But to sort of make it clear, let's say that we have an example where in our program we set some variable a equal to 2 and some variable b equal to 1. And then let's say one of the threads that we generated sets a equals 5. It's like, okay, my job is set a equal to 5. And then some other thread says, okay, my job is add a to b, and then set that equal to b. What is the problem here? What is a potential problem here? What might be the issue? Yeah.
The order that a gets updated.
Exactly. And specifically, what are the two possible outcomes here?
Well, if it's just going to be b plus 2, or it's going to be b plus 5.
Yeah, you got it, exactly. So in this case, the tricky part is we don't know what b will end up as because it depends on which thread is executed first. And so this is something known as a data race, or related to something that you guys might have heard of called a race condition. And this is something that you will become intimately familiar with in CS 110. I believe not 107, just 110, if you continue on to those classes. But we will only be getting into the basics here. Okay, does anyone have any questions so far, sort of on the basic idea of multi-threading? No. All right. Okay, so this brings us to the idea of locks. So we've actually already seen locks, and Avery sort of gave a brief explanation of what they were, and we saw them with RAII. Whereas before we had this lock known as a mutex that we could lock and unlock, we realized, okay, there's actually a better solution where we wrap it in a lock guard, and that automatically ensures that the lock will always be unlocked when the item is destroyed. So something I want to do is I want to give you a look at, again, how multithreading works in C++. And so to do that, we're actually going to be returning to our favorite, the standard library. So I'm going to click the link. Awesome. So it turns out that multithreading is such a core feature of a program that it's actually one of the core headings under the C++ standard library. So at this link right now, we see sort of the 5 main parts of it, and there are just a couple of things that I want to emphasize from each part. So the first is the atomic heading. Sort of the thing to take away from this atomic header is if you are working with multithreading in your programs, what you want to use are not ints, bools, strings, anything like that. What you'll actually want to use is this atomic equivalent. So you'll notice if you look at this link, rather than bool, they have something known as atomic bool, and rather than int, they have something known as the atomic int. And really what this is doing is it's telling us this is a class that's supposed to guarantee that there are no data races within an individual variable type. So to make that a little clearer, what exactly does that mean? You'll recall that something such as in our example we had b plus equals a. It turns out that this simple addition operation is actually a sequence of sort of multiple instructions under the hood. So really, although it reads as a single line of code, b plus equals a, what it's doing under the hood is really something like retrieve value of a, add a to b, replace value of b with the new value of b, something like that. So there's sort of a sequence of many different things that it actually has to do to execute this one line of code. So what the atomic class, infinite recursion. Let's see. Yeah, there we go. All right, so what this atomic class is doing for us is the C++ designers have already provided us with a class that ensures us that basically what we expect to be a atomic operation, in other words, an operation that does everything at once, is in fact an atomic operation. So for example, if we were to use, if say b and a were atomic ints, then to add b plus equals a, we could instead use this method called atomic fetch add. And really, that's just the equivalent of the plus sign. So you can go back and read through these. Again, this is if you ever want to program something yourself using multithreading, these are the variables and the functions that you'll want to use. A couple other things that I want to reference in the library.
I just want to clarify one thing.
Yes.
Like, if you want to do a long equation, you have to call the entire method to. Okay.
Right. Yeah, and so another thing is that you won't necessarily have to use, even when you're writing a multi-threaded program, you won't necessarily have to make every operation an atomic operation. So it's really only in the cases where the order in which things are executed really matters. In that case, then that's where you'll want to use atomic operation. But in other cases in your program, maybe it doesn't matter and you won't have to use it there. Yeah. All right, so the thread class in the STL is sort of what we were just working with. So we're actually going to be getting to a code demo of that later, so I'm going to skip that for now. One thing that I wanted to bring up, so we had a really good question last time, which was, so we introduced this concept of lock guards, and someone asked the question, is it possible, so it seems like there's sort of this weird issue where the lock guard is only unlocked when it goes out of scope, but it seems like you might sort of want to unlock and lock within the function. And what we said before was, okay, what you can do is you can just use these sort of scope operators where you just insert literally 2 curly braces to form a new scope. That is actually one perfectly valid solution. It turns out there is another solution. So I would like to append to my answer to that from last time. a lock guard is one of the wrapper classes that you can use to wrap your locks and still have them RAII compliant. There's actually another type of guard called a unique lock, and that's this one right here. And what that does is it actually does the functionality that we were looking for last time, which is it allows you, when you declare the lock guard, you can either lock or unlock it. Within the function, you can lock or unlock it, but it guarantees that when that guard goes out of scope, it will definitely unlock. So sort of, it does the same thing as the lock guard, except you're able to lock or unlock in the middle, but it still guarantees that your lock will be unlocked at the end of the scope. So yeah, I wanted to bring that up because someone did have a great question about that. So there is in fact something in the library that allows you to do that. Yeah, any questions so far about those two classes? Yeah, this is parts sort of exposing you to what's in the standard library so you know what to look for if you're trying to write your own program. And then sort of the second half of this will be more conceptual of like, okay, how do you work with multi-threaded programs? Yeah, and why are they interesting? Yeah, okay, let's see. So these last two, I won't go into them much. Condition variables you'll work with a lot if you continue on to later CS classes. You can think about them as a way for two threads to communicate with each other. So condition variables allow you to either signal or wait for signals. So yeah, condition variables are a way you can think of for two threads to communicate back and forth with each other while they're running. This future class is sort of interesting. Has anyone worked with JavaScript before? Okay, a little. Okay, yeah. So in JavaScript, there's this notion of an await, or asynchronous functions in general. It turns out C++ has this as well, and that's in this future class right at the bottom here. So yeah. So just to give you a heads up that if you ever do need asynchronous functions, you can use the future class. And for a brief overview of what asynchronous functions are, you can imagine them as sort of, you can imagine them almost as a way to launch your own thread and wait for a response from that thread. So what would happen normally is you would do something like, let me send a web request in a new thread. And so it'll sort of construct the web request and send it in a separate thread. And only when it receives the response will it return to your original thread with the response. So that's sort of the idea of asynchronous functions. And yeah, no worries if you haven't heard of that before. It's something that's commonly found in languages like JavaScript. Yeah. Are there any questions about that so far? No. Okay, perfect. In that case, what we will do is, yes, okay, so this slide lists pretty much what I said. Again, lock guard versus unique lock. There's a couple different types of locks, of so-called mutexes that you can work with. Yeah, so one interesting one is the recursive one, which says that a single thread can get a lock on that thread multiple times. So sort of, you can imagine it would be like calling, like having this chalk, but being able to claim ownership over the chalk like 7 different times. And then to release ownership of the chalk, you would have to say, I release ownership of this chalk 7 times. So that's sort of the idea of a recursive mutex. Again, sort of just to give you a broad scope of what is out there for you to work with and play around with. Okay, so now I think we will be getting to sort of the interesting part, which is seeing multi-threading in action. So before I go to code, does anyone have any questions about sort of the conceptual things around multi-threading, locks, data races? Okay. Yes, Brian.
When you implement a timer, do you have to use this?
Yeah, so when you implement a timer, do you have to use this? So actually, if you continue going on through all sort of like the systems classes, you actually will end up implementing multiple timers, which is kind of funny. But yeah, absolutely. So timers work in a similar way to this. Depending on how you implement them, they'll likely be using what we mentioned about condition variables, which rely on being able to wait for signals or signal other threads, things like that. Yeah,
I'm still confused on how the atomic thing works, like, instantaneously. Like, in the end, which do we get?
Yeah, right.
B plus A equals 5.
Yeah, so that's a great question. So in this case, we still, so using the atomic class, and so again, so for the recording, the question was, how does the atomic class, like using atomic variables and atomic methods, actually affect this scenario right here? In this case, it actually doesn't. And the reason why that is because in this case, the only operations that we're calling atomic are sort of the plus equals in itself, or like the A equals 5 in itself. But we aren't guaranteeing that something like A equals 5 and then B plus equals A is atomic as a whole. So using that class, in this case, would still end up with us having either value of B. Where you can imagine it might be more important is in things where, and this is a situation you'll definitely see it in CS 110, it's sort of something known as like the got milk situation, where the general concept is, let's say it's you and a roommate living in a house, and you come home one day, open the refrigerator, and realize that you're out of milk. And so then, of course, you go off to the store to buy one. But the problem is, while you're off buying the milk, your roommate comes home, checks the refrigerator, sees it's open, sees it's empty, and then it's like, oh, okay, I better go to the store and buy milk. And then now you have 2 milk, which is way more milk than you ever want. So in that sort of situation, you'll find out that the reason why that doesn't work is because your check for whether you need something and then you're actually fulfilling that need is not atomic. And so you can use, sort of by analogy, you can sort of use atomic operations like this to ensure that they're atomic. In that case, particular case, I believe you still wouldn't be able to because it's not something as basic as like a plus equals. Yeah, but what this guarantees is that, for example, when you check the value of A and when you store the value of B, it's still consistent. Yeah, good question though, good question. Yeah, any other questions? Okay, all right. So in that case, let's see how threads work. So we are going to go to this file. Okay, so right here, I have a file. It doesn't have much, but I've imported some of the libraries that we'll need. So the idea of this is, I'll write a bit and explain as I go what I'm doing. So the idea of a thread is this. So let's say that we want to have 2 threads. So the way that we're going to use them is, again, using this thread class. Let's call them thread 1 and thread 2. So the way that you use a thread is you can sort of imagine them as workers. You can imagine them as sort of like the people that volunteered for a demo earlier on. And so what a thread always needs is it needs what job it's trying to do. So in this case, let's say we're going to define a function called greet. And the only job of these threads will be to run that function, and then once it's done, return. So in this case, we'll say greet, and then let's actually write that greet function. And the second thread will be doing the same thing. So let's write a function greet, which will take in, let's say, some int I, which will be like an ID for which thread it is. So let's call it int ID. And all it's going to do is, let's say, it'll see out, hello there, my name is... Okay, and then that's all it does. So going back to the syntax of how you declare a thread, so again, whenever you declare a thread, you want to tell it what job it has to do, which in this case is the greet function. And then syntax-wise, all you do is you pass in the parameters to that function after that. So in this case, there's only one parameter, the ID, so let's call that ID1. And then for this greet function right here, let's call that ID2. And here, let's actually do greetings for my threads. So the way that you can imagine how threads work in your program is that as soon as you declare a thread in your program, it will immediately start trying to execute its job. So as soon as you declare std thread 1 greet 1, it'll immediately sort of go off to the races and start trying to see out what it's trying to see out. And the same thing when you declare thread 2. So let's see what happens. Okay, so actually before we do that, so at the very end, let's see out all greetings done. And okay, so can anyone give me a guess of what will happen if I try to run the program right now? This is sort of tricky. So specifically, do you think it will see out anything? Anything besides greetings from my threads? And all greetings done.
They probably won't even see out that because you have used this undeclared identifier hours.
That's a great point. That's the exact question. That's the exact question. Even better. All right. All right. That was the warm-up round. Good job, you guys. All right. So let me restate my question. How many people think that "Hello there, my name is 1" will be c-outed? Everyone's like, this must be a trick question. How many people think "Hello there, my name is 2" will be c-outed? Okay, yeah, no, that's fair. If you don't think 1 will, then 2 won't. So, in fact, your guys' gut instincts, in some sense, give me 1 second.
Why is it Greek comma 1?
Yeah, so that's sort of just the syntax for declaring the thread. Let me just do this. Let's see. Oops, no, I did not mean to do that. Yes, okay, so the reason for that is because, there we go. Question mark. Perfect. All right. Okay. So to answer Brian's question, the reason why it's Greek comma 1 is just syntactically the way that you pass in the job to your worker is by listing the name of the job and then in commas afterwards all the parameters needed by that function. Yeah, so just a syntax thing. Okay, so this is sort of interesting. So there's a lot of things going on here. So first is notice, okay, we did print greetings from my threads, and we did print all greetings done. But all greetings done happened before any of the "hello there, my name is." And then furthermore, sort of the 2 c-outs are sort of very, very all over the place. So let's ignore those for now, and let's just focus on these 2. Why is it that all greetings done occurred before any of the 2 hello there c-outs? Yeah, he's...
Would it be that c-outing directly from names is like faster than calling a function to c-out functions?
Yeah, exactly. And sort of the more general idea of that is we can't forget that main itself is still a thread that's running. So if you remember from our diagram earlier, we had sort of the 2 threads that split out, but the main function still was also running in the middle. So yeah, so that's sort of the general idea. And in fact, my question earlier was sort of a trick question. Sort of the hard thing about data races is that they're unpredictable. And so we actually can't predict whether the main function will sort of finish entirely before any of the c-outs happen or whether it won't. So to make that a little clearer, we can use, let me double check that I'm getting the syntax right. We can use... so this is a function also in that std thread class right there. And what it does is it allows us to tell a particular thread to sleep for a certain number of seconds. So let's make it sleep for 5 seconds, just to be safe. So now what I expect from this is that I fully expect the main thread to return before any of these 2 threads can execute their cout statements. So let's test that hypothesis. Okay, perfect. Can anyone tell me why adding in the sleep statement actually sort of helped me make it more of a guarantee that those 2 couts wouldn't print? Why is that? Oops. Yeah. Absolutely, that's exactly right. So to say that one more time, so because we're sort of forcing these 2 threads to wait, we're sort of making sure that our main function finishes first. And what happens when our main function finishes is that those 2 threads go out of scope. Because exactly as Byron noticed, sort of we declared these 2 in the main function, so once the main function ends, the 2 threads are also out of scope. And that's why we were getting as well the this error right here, terminate called without an active exception, which is complaining that those two threads were terminated for some unknown reason. All right. Yeah, does anyone have any questions so far? Sort of on basic thread uses? No. Okay.
Wait, so like, can you put multiple things into a string at the same time?
Yeah, so that's a great question. Can you clarify your question one more time? So put multiple things into.
Because like, this time I noticed you didn't have, when you ran it, like, actually wait, the last time you ran it, you had like T2 T2 terminate because like the 2 went into C.
Exactly.
C out, like, while you're still trying to see out the other things. So like, you see out can take multiple things at once automatically.
Yeah, so this is a great question. So the question is, why are these outputs sort of overlapped? Why does this terminate overlap with this my name is 2 cout? So the answer to that is, take a look one more time at cout. Do you think this line is an atomic operation? Who thinks yes? Who thinks no? Okay, can someone explain why? Written in back. Yeah, so essentially even just looking at this one line, we'll notice that we actually have multiple operations going on here. So notice that even just explicitly, we have three different sort of equivalent of like adds going on in this one line. And remember that's because this insertion operator returns the stream itself, and that's what allows us to sort of chain cout expressions like this. So that's exactly it. So we aren't guaranteed that this one line will execute all at once. So actually, I'm going to ask you guys, what is a way that we can guarantee that all of these couts will happen at a single time? What do you think is something that we could use? Say it louder. A lock. Okay, I don't know if that was much louder. But there we go. We amplified it. Absolutely, a lock. Okay, so we could do something like, let's say we have a, so this is called a mutex. So let's call it some mutex. And then how do we want to declare this mutex? So one idea might be, okay, we could just say something like this. Does this raise any flags for anyone? Okay, Mason, what's up?
Not RAII compliant?
Absolutely, yes, exactly. So how do we want to make it RAII compliant? Perfect, exactly. So once again, sort of the syntax for a lock guard, and again, one more time, sort of the idea of all of these, how to make something RAII compliant, is this idea of wrapping it in another class that can handle the destructor and constructor for us. So in this case, the syntax for that is, let's use a std lock guard. So it turns out the lock guard is actually a template class because it can take in the recursive mutex that we talked about. It could take in the timed mutex. So that's why we have to put in mutex. And it has to be std. I could also just declare std mutex up there, but and then we'll call that, say, lock guard, and then in parentheses is where we specify the lock that we want to guard. So in this case, it's this mutex. Awesome. And then notice I don't have to do any sort of explicit unlock because the lock guard, when it goes out of scope right there, will take care of that for me. Okay, now who thinks that the couts will look nice? Okay, but how many think the couts won't look nice? Okay, a couple. Okay, nice. I think the joke we always make in this sort of situation is about the voting ratio of the United States, like 3 people out of 10, something like that. All right, awesome. So so we still actually haven't solved the problem of the main function ending first, which is why this still overlaps. But you'll notice, disregarding that, the hello there, my name is 1, and the hello there, my name is 2 do execute perfectly. So let's actually... Yeah, so that T is actually from this terminate message. So let's actually, to make it less confusing, and because this is important, let's actually fix that message. So once again, the problem is that right now our main thread is finishing before any of its 2 threads can finish itself. So the way that we fix this is that we have to tell the main thread to explicitly wait for its threads to finish running before we want it to finish. And so the way that we do that is that the syntax for that is just we take the thread that we want to wait for, and then it's a function called join. So you can think about it as, okay, we want to wait for thread 1 to rejoin the main thread, and thread 2 to rejoin the main thread before the main thread can continue executing. So what will happen is that this main function will actually wait here until thread 1 has finished, and wait here until thread 2 has finished before it continues on to any of the other lines. Okay, so let's see what happens now. And we finally have the program that we expected to have. Okay, so question, just to confirm understanding, can these 2 lines have been switched? The hello there, my name is 1, and the hello there, my name is 2. Who thinks they could have actually ended up in the opposite order? Who thinks they could not have? It must be 1 then 2. Okay, explain why you think they must be in the order. Either you. Yeah.
Thread 1 first. Thread 1 dot join first.
Okay, yes. So this is a perfectly valid assumption from the way that we've written it. So this is a sort of tricky thing, which is why I wanted to bring it up. And I'm sorry, most of the questions usually are trick questions. This one happened to be that. So this is actually a really common misconception, which is why it's really important to bring up as well. So even though the main thread is waiting for thread 1 to join before it waits for thread 2 to join, the threads themselves can end at any time. So another way to demonstrate is, let's say this main function actually had let's do a lot of really heavy lifting work in between. While it's doing that heavy lifting work, it's likely that at some point these 2 threads finished. So actually what this join call is doing is it's actually really sort of, you can imagine it as just checking this boolean of, has this thread finished at any point before this or not? If yes, then okay, I can immediately return. If no, then I have to wait here until it has. So in this case, these 2 threads can execute at any point, but it's true that the main thread won't check for whether thread 2 has finished until thread 1 has finished. Does that make sense? Because that was a little tricky. Good. Okay, I'm seeing thumbs up. Very nice. Okay, yeah, we're slowly making our way through sort of all of the most essential facets of threading. So this is very nice. Okay. So something else I want to emphasize is that, again, we've only been working with 2 threads so far, but this can actually work with any number of threads. So let's say we had some constant up at the top. Let's say we wanted 10 threads to run. Then instead of declaring each thread explicitly, we can use something even as old as a vector. So again, we can actually have a vector of threads. So a thread, again, is just any other class. Just like any other class, you can use data structures that we've learned on them. So we'll call it a vector of threads, and then to initialize them, sort of as we expect, for I is less than k num threads, we're going to do threads.pushback, and then the same as before. In this case, if we wanted to, we could use sort of the uniform initializer that we've learned so far in this class, but we don't have to. So this default initializer, just like before, we pass in the function and then the ID. And then one more time at the end, we want to do, we have to wait for all of those threads to return. So we're going to do std thread, t for threads, and then t.join. Okay. Are people clear what we just did? Yeah, okay. So sort of to, again, test for understanding, what would have happened if instead of having this separate for loop here, it seems like, oh, why do we have 2 for loops? What if we had just done, say, threads I.join right here? What would have been the issue? Yes, please. Exactly. So again, louder, it would have called one thread, then waited for it to end, then another thread, then waited for it to end. And you'll notice what that sounds like is exactly serial as in non-parallelized execution. So really what you just did is you actually just wrote sort of the same serializable program as we've been writing up till now. Exactly. So that's why we first want to launch all the threads so that all of them can be executing at once, and then at the end we want to test that all of them have joined. Yeah, Byron.
This is a random lecture, but so what controls the switching between the threads?
That's a great question. So what controls when does each thread basically what controls how the threads are executed, in what order they're executed in. So that actually is the subject of a lot of research. Yeah, and in fact that's a topic that you'll cover extensively in future systems classes if you go on to that. So that's actually a very essential question. And sort of a general idea of how that works is there is some sort of scheduler in your CPU that is in charge of scheduling which threads go on at once. And sort of to give a sense of like how that works, you can imagine actually that the time slices that each of these threads are being given on the CPU is actually really short usually. You can imagine sort of like each thread is given like thread 1 is given 1 millisecond, then thread 2 is given 1 millisecond, then thread 1 is given 1 millisecond to try and sort of execute as much as it can. And then the role of the scheduler, which is sort of its own special kernel thread outside of any of these threads, is the scheduler is in charge of figuring out which one to put on next and how to save the state of each thread while the other threads are running. Yeah, and then so sort of all these sorts of algorithms for how to best schedule different threads, things like that, that's actually the subject of a lot of research. Yeah, that's a good question. Yeah, what's
so
up?
for the second for loop, why is that standard thread and
Yes, actually, that was exactly the next question I was going to ask. So great question. Yeah, so why do we have this thread and here? What is so important about the and? Or is it important at all? Yeah, Mason.
It's a thread reference, so because the threads probably aren't copyable, right?
Yeah, so you can imagine what would have happened if we didn't have the and. Then you'll remember that each time, well, for one thing, you'll notice that it has an error message called to delete a copy constructor. But the reason why that is because remember that when we don't pass by reference, what are we passing by? Copy. Yes, even louder. Yeah, exactly. Pass by copy. And what happens when we declare a new thread? What did we just say happens when we declare a new thread?
It starts running immediately.
There we go. So exactly. So if they hadn't deleted the copy constructor, then what would have happened here is we would actually be launching 10 new threads because we just copied 10 new threads. Yeah, exactly. So that's why we have to pass by reference there. And the ampersand is just indicating that we're accessing it by reference as opposed to by value, by copy. Yeah, great questions. All right. So we can see that running just to make sure that we are running that correctly. And that's perfect. All right. And I believe that system error, I'm actually not sure where that's coming from. I'd have to take a look. But okay, so that's sort of our crash course on multi-threading in C++. Do you guys have any questions so far? Yeah, go for it.
is there a difference between multithreading and multiprocessing?
Yeah, so the difference between multi-threading and multiprocessing is sort of exactly the demo that we started off class with, which is sort of, they also sort of, actually that's sort of a more detailed answer as well. They do have different benefits and non-benefits, like for example, processes are a lot more isolated from each other than threads are, things like that.
So the beginning demo was of multithreading itself, but what with multiprocessing?
Exactly. So multiprocessing, you can sort of imagine it as like a larger version of multi-threading, but with a couple of other additional features. And we can maybe talk after class about that. Yeah. So and also if you search online, sort of what's the difference between multi-threading and multiprocessing, you'll get some answers. But yeah, that's actually a sort of nuanced question. Yeah, which is good. Yeah. Did you have a question, Byron?
Yeah, is there any tools you recommend for like viewing like how many threads are running at a time? One of the problems I know out there is like if you have too many threads, right, you just spend all your time switching between threads and no actual.
Right. Yeah. So are there any tools for being able to view multiple threads running at the same time? So it is definitely possible to view threads while in GDB. I'm forgetting the exact syntax though. So it's definitely possible within GDB. I'm wondering whether there are any other pieces of software out there. I would almost guarantee it. But I can also take a look after lecture and see if there's anything that I can find on it. But absolutely in GDB. Yeah.
I remember in Linux there is something called htop that you can check all the running process and threads.
Right. So that checks all the running processes. And did you say it also checks the different threads? Okay. Okay, perfect. So it looks like, is that a Linux command you said? Okay. Okay, yeah, exactly. htop. htop.
Or just top. It's just for
Oh, top as well. Oh, yes. Okay, of course, of course.
Htop is like a colorful one. You can see different colors.
Got you.
It's like, ooh, CPU usage, but then it's like bar percentage.
And I think it gets red like the.
As you use up. Yeah, absolutely. Yeah, thank you. Thank you. That's a good reference. Yeah, Brian, did you have a question as well?
Never mind.
Okay. Awesome. Yeah, so I'll post this code to the website again after lecture. So we only have 4 minutes left, so I was going to actually talk a bit more about RAII, but what I'll do is I'll just sort of skim through that and let you guys know what to look out for, and if you're actually interested, you can go back and learn more. But first, announcements. This is our last class, so I wanted to give you guys a round of applause for being awesome students and sticking with us throughout the entire quarter. So give yourself a pat on the back. And I hope you guys all recognize each other by now and will wave hi to each other on the streets. Yeah, and then also on behalf of both me and Avery, keep in touch with us afterwards. Email us at any time. Even though our Piazza may become deactivated, the Piazza in our hearts will always be available. So yeah, come email us at any time. And yeah, we would love to keep in touch. Yeah, and we will also wave hi at you on the streets. So again, thank you guys. So I'm going to give, again, a brief overview of just what to look out for in these slides if you want to go back into RAII. Sort of the big idea is, once again, the way that we make something RAII compliant is by using a wrapper class that takes care of the logic of destroying something after the object goes out of scope. And we saw last time that there were 2 ways to do this with pointers. We could use a unique pointer or we could use a shared pointer. And I would think in your mind, what's the difference between the 2 again? There's one sort of tricky thing in here, which is how do you make a unique pointer or a shared pointer? Right here we have one way of making it, but I'm actually sort of the big takeaway of the second half of class is this is actually not the way that you want to declare a unique pointer or shared pointer. In fact, the way that you want to declare it is by using these 2 built-in smart pointer creators. Creators is not an official term. They just don't have an official term, so I made up one. Specifically, there are these 2 functions, make unique and make shared. So whenever you're trying to make a new unique pointer, what you want to do is you want to say make unique of that type or make shared of that type, as opposed to passing in this new node. And then really all of these next slides are about why that is. And it's actually very interesting. If people are interested, I might actually just host a small brief talk during week 10 sometime to talk about it, because it's just a really interesting piece that actually goes into race conditions. So it very much relates to what we learned about multi-threading. But yeah, you can also go through the slides. The takeaway though is that you essentially always want to be using the make unique or make shared as opposed to explicitly saying new node. And one of the benefits of that is that we can essentially say to programmers that in C++, we can now almost never call new or delete. Even when we're working with things like raw pointers, even if we still wanted to use something like int star, that int star will almost never come from us explicitly calling int star n equals new int. That it'll always be sort of a reference to another existing reference. So so this is sort of one of the big takeaways. Again, one of the biggest new concepts to come out of modern C++ is that we essentially have gotten rid of new and delete. Which is very cool because it eliminates a lot of sort of memory leak issues that have plagued C++ in the past, and that lead to a lot of security vulnerabilities. So with that, one question that someone asked on their forum was, where do I go from here? Like, how do I continue learning more about C++? Like, what happens if I want to learn new things? So first, the best way to continue improving your skills in C++ is to just use C++. So in whatever personal projects you want to build, or wherever you go off to work or in your classes, yeah, use C++ more, use modern C++. And then if you're actually interested, there's a lot of C++ reading you can go into. The ones that I would recommend are sort of these top 5. And it's not that you have to read all the top 5, it's that sort of take a look at which one is interesting. For example, Effective Modern C++ sort of gives like a nice overview of what are sort of the key new features of modern C++. Another good online resource is this guy Herb Sutter, who's one of the co-creators of C++ essentially. He writes a really nice online blog. So if you search Herb Sutter C++ blog, you'll find his blog, and that sort of explains a lot of the unique features of C++ and sort of a lot of the tricky points of C++ to watch out for. So with that, thank you all very much. Congratulations on finishing. Oh man, yeah. And logistics-wise, we will still be holding office hours next week for assignment 3 if you're interested in. Yeah, and I may or may not hold a small talk to finish the second half because it's sort of interesting. But good job, you guys. Have a great Thanksgiving. And good luck with finals.
Wait, when
Yeah.
we do triple pointers, can we do like unique shared?
A unique shared pointer. You totally could. So what you would have is you would have a unique pointer to a shared pointer to a shared pointer. Yeah,
So
quite
theoretically,
interesting.
on my midterm, I don't have to use numerically different.